Firmware Guy presents PinChange interrupts on the Arduino. The PinChange interrupts are needed on the Tricopter project to interface with the digital RC radio. If you already understand the basics of digital RC radio, you can skip and go directly to the PinChange interrupt video where I do a code review of what I've written. If you don't understand how a digital radio works, I'm going to introduce the basics in the next couple of slides. For the Tricopter project, I've selected a basic 6-channel radio. I picked it up on Amazon for less than $100. It's a FlySky FS-T6. It's a basic radio, got fairly decent reviews. The first 4 channels represent the standard controls you'd think of on any RC plane. Roll, pitch, throttle, and yaw. There are 2 additional channels left. I haven't decided what I'm going to do with those. I'm sure I'll integrate them somehow. But the basics of an RC radio are, for each channel, it puts out a 1 to 2 millisecond pulse at a repeating interval of 18 to 20 milliseconds. And the pulse encodes the control output. So the width of a pulse translates to a particular control request depending on the channel and the pulse width and the width of the pulse. Here's an idealized picture of what a pulse train for a digital RC radio looks like. So you've got the individual channels, ailerons, elevator, throttle, and rudder. So that'd be roll, pitch, throttle, and yaw. And for each channel, every 18 to 20 milliseconds, the receiver outputs a 1 to 2 millisecond pulse. Each pulse represents a certain control position. So what they do is they take a 1.5 millisecond pulse as the middle of the control throw. So if the aileron channel was outputting a 1.5 millisecond pulse, there would be no commanded roll. In other words, all the control surfaces would be neutral. The same is true for the elevator. The throttle's a little different. A 1.5 millisecond pulse would be half throttle. 1 millisecond being minimum throttle, 2 milliseconds being maximum throttle. The rudder is similar to the ailerons in the elevator in that a 1.5 millisecond pulse would be a neutral rudder position typically. This slide kind of summarizes what I covered in the previous one. So you can see for all the control surfaces, a 1.5 millisecond pulse is neutral for rudder, elevator, and aileron. In the case of a rudder, a 1 millisecond pulse is right turn. The elevator, it's pitch up. And for ailerons, it's turn to the roll to the right. For a 2 millisecond pulse on the rudder is a full left turn. On the elevator, it's a pitch down. And on the ailerons, it's roll left. Throttle, like I said previously, is a little bit different, but this kind of gives you an idea of as the pulse width increases from 1 millisecond to 2, you get an ever increasing percentage of throttle. The next 3 slides are logic analyzer traces of the rudder control signals from the radio receiver. And all it's showing is basically what I demonstrated on the previous 2 slides, but they're actual pictures from a logic analyzer instead of pictures I've drawn myself. So they do show that the signal or the pulse width varies from approximately 2 milliseconds, 1.96 milliseconds here, down to approximately 1 milliseconds for the last slide. Rudder neutral example. Rudder right example. Here's the code for the PinChange interrupt. And this code's structured basically in 3 different parts. There's all the generic code that is common to both the Arduino Uno and the Arduino 101. And then there are sections that are dedicated to the dependent parts of the code related to those individual boards and micros. Okay, so I always put a header on, what the name of this is, and some of the inputs. In this case, the inputs are all the digital RC radio, and what the goal is. The goal is to measure the pulse width of the control signals of a 4-channel digital radio. Okay, so the first part here is a series of equates that defined what the 4 channels are. So we've got roll, pitch, throttle, and yaw. Following that is a 4-element array that maps each of the logical channels, so roll, pitch, throttle, and yaw, to a physical pin on the Arduino. And I'm going to use the same pins on both the Uno and the 101. What follows next is a variable that holds the pulse width calculated by the interrupts for the various channels. Next is a control flag that denotes when the various channels in pulse width are valid. So if none of these bits are set, none of the values in pulse width are valid or are the most recent. If all these bits are set, then the program believes one iteration is complete, and it's okay to read all the pulse width values. If one bit is set, you could read that one if you had wanted to. Okay, and here's the setup routine. So the setup is pretty simple. We're just going to do a config pin change for receiver. So this will configure the interrupts, and it'll vary depending on what board you're going to use, and then enable the serial debug port. This is the loop, and what I do, above the main loop, I always put a comment block that describes the various steps. So we're going to clear the control variables, wait for the interrupt to update all 4 channels, copy the pulse values from the variables updated by the interrupt to the ones that are local to the loop, so that you don't have to be in a rush. You don't have to worry about the interrupt trying to update them. Output the values to the console, wait a half a second, and go to number 1. And then you'll notice these bulletized numbers. Well, down in the code, those bulletized numbers map to the code down here. So this is how you're going to clear the control flags. Now you're going to wait until all the channels have been updated. So you cleared all the bits in the control variable. Then you're going to wait until they're all set. And that's what this line does. And then as soon as the program determines that all the bits are set in the control variable, it's going to copy all the individual pulse widths in the variable that the interrupt updates into a variable that's local. Then it's going to print those out by channel, by channel. Delay a half a second and then do it all over again. Okay. Rising edge is a variable that, as the name implies, captures the time of the rising edge. So basically what the interrupt is doing is that for each channel, as the channel goes from a logic level 0 to a logic level 1, it captures the time that happened. When that same channel goes from logic level 1 to logic level 0, it captures that time, but it also calculates the pulse width by subtracting the falling edge time from the rising edge time, and that gives you the pulse width in microseconds. So that's what that variable is used for. Okay, so now to configure the interrupt for an Uno, you have to enable 2 interrupts because of the way the pins that were chosen were across these 2 interrupts. So pins 2, 4, and 7 are on these particular bits. Pin 8 is on that bit. So you have to set bits in those 2 masks and set these interrupt bits to enable to get pin change interrupts for the pins of interest. Okay, so pin 8 is by itself on this interrupt. So I don't have to do any determination. I know if I got an interrupt here, it's for pin 8, it's the yaw channel, and I just call the pin changed. And this routine determines if it went from low to high or high to low. Okay. Let's see. And then here we go. This is another comment block that explains sampling the timer, sample the current value of the pins of interest, XOR the current value of the pins with the previous values of the pins so you know which ones have changed state. Because for this interrupt, it's for pins 2, 4, and 7. And I don't know which of those pins changed. So what the program does is it keeps an image of the pins from the previous interrupt, compares it to the image of the pins from this interrupt, excuse me, and then using an XOR determines what's happened. So 0 XOR 0 is a do nothing, as is 1 XOR 1 is a do nothing. In other words, that pin didn't change. But if the pin went from a 0 to a 1 or from a 1 to a 0, we've got to either calculate the rising edge or calculate the pulse width. So that's what this code does. Now let's go through it. So we'll go down here to this, and we'll, in order to take and minimize the impact of code execution time, one of the very first things we're going to do is we're going to grab the time stamp. So we're going to capture the time that this interrupt was called in microseconds. Here we're going to grab the image of the pins. We're going to exclusive OR the image of the pins on the D port with the pins on the D port previously. Now we have the pins that have changed. Now we're going to go through each channel in this for loop and look for those pins that have changed. So this code here will check to see if the pin has changed, and if the pin has changed, we call the pin changed routine. If it hasn't, we'll loop again until we do, or until we're done. And then the very last thing this interrupt does is it updates the pin D previous. So we take the current image and make it the past image, so that the next time this interrupt is called, this is current. So that's the end of the Arduino specific code. Now, we have some common ISR code. So this is the pin changed code that we've called earlier. It's also called by the Arduino 101 code, specific code. So this takes the channel number as an input, the timestamp, and which pin, or the pin value, I'm sorry. So if the pin value is high, that means we got a rising edge. So we capture the timestamp gets captured in the rising edge of the corresponding channel in the rising edge array. If pin val is not equal to high, that means it's a low. That means it's a falling edge. And once again, we'll calculate the pulse width by using this timestamp now, subtracting the timestamp from the rising edge, and subtracting the two, and that gives you the pulse width. Then we'll update the channel and we exit. So that's the end of the common code. Now, for the Arduino specific code, this is a little more straightforward and easier to follow. We use the standard library routines to attach the interrupts. So first thing we'll do is we'll make the channels pin modes as inputs. We'll attach an interrupt for each pin. Now, one thing that's nice on the Arduino 101 is you'll see here there's an interrupt assigned for each channel. So we don't need to go through and figure out which channel caused the interrupt. We know because the code landed here that we can execute for that specific channel. So there's an individual interrupt for roll, pitch, throttle, and yaw. And it executes the same code that we talked about before with no changes. Well, that concludes my code review of the pin change interrupt. If you have any questions that I didn't cover or you need further explanation, please comment below. Thank you. Bye-bye. Thanks for watching my video. If you enjoyed my presentation and found it useful, please subscribe. All the examples that you will see and links to the current documentation can be found at www.firmwareguide.net. Thank you. Bye-bye.